Let's take a look at the F distribution here. Now, this table is a 4-pager. There are 4 pages to it. And the reason for that is that there's 2 different kinds of degrees of freedom. And I'll explain those as we go through the ANOVA test. But you have degrees of freedom in the numerator, and we'll abbreviate that, degrees of freedom in the numerator. And then over here, we have degrees of freedom in the denominator. Turns out that the F statistic is going to be mean square treatment groups mean square error. And it's a fraction. And so the top number comes with the degrees of freedom in the numerator, and the bottom number comes with the degrees of freedom in the denominator. So numerator, denominator correspond to our test statistic. Now, you can see the degrees of freedom in the numerator, 1, 2, 3, 4, 5, 6, 7, 8, but that's all that they could provide for this one. And then you have the degrees of freedom in the denominator going 1 through 8. That's not many different types of degrees of freedom. So the next page is a continuation of this one. It's actually, if you put all 4 of them together in different quadrants, you would have just a really big table. But you can see that in the second page, the degrees of freedom in the denominator are the same. But the degrees of freedom in the numerator continues from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then eventually it starts jumping by much more until you get 1,000. So that's the first 2 pages. And then the last 2 pages continue the table down. And so, I don't know if you can see this, but so this one, you have degrees of freedom in the numerator 1 through 8 here. But then if you extended the table, you'd have degrees of freedom in the denominator stopping at 8, then picking up with 9 and going through 1,000 there. So if you put these 4 together, you create, you're not going to be able to see it, but it really would be just one big table. So you're going to have to specify the degrees of freedom in the numerator and degrees of freedom in the denominator. And all of these numbers, just like all the chi table and the t table, all of these numbers are critical values, and they're used in the classical approach. And it turns out that the F distribution is skewed for most of the tests that we do. The F distribution will be skewed just like the chi-square distribution. So that's the F table. Let's do an example. And let's say that we're going to do the classical approach. And I'm going to show you how to calculate degrees of freedom in the numerator, degrees of freedom in the denominator. But let's say that this is the F distribution. And we have degrees of freedom in the numerator is 7, and degrees of freedom in the denominator is equal to, okay, your classical approach. Here would be your alpha, the shaded region, this critical region. Let's just say it's, for this one, let's do 0.01. If you find a test statistic, and the test statistic that we're going to calculate is the F. This is the one that you want to plot on the horizontal scale. And the test that we're going to use to get that F statistic is a test called ANOVA. And that stands for the analysis, it's an acronym, of variance. So we're actually going to look at the variances of different numerical data sets, and based on the variances, which are closely related to the standard deviations, based on those, that's how this test statistic is calculated. Now, this number right here is the F of 0.01. This is what we call the critical value. And we're going to get this one by going to the F distribution table. And you can see here it's table 9. IX. Okay, go find the critical value. Go ahead and put it in the chat. The F distribution is another one that starts with, because variances are positive, and so if you take one positive number, these are actually variances here. If you take one positive number and divide by another positive number, you have a positive number, and so the F distribution is always positive. So like the chi-squared distribution, this one also is going to start at 0. You've got your critical value, which is another reference number along the horizontal scale, and then you plot your test statistic. Sometimes it's going to fall in the critical region, sometimes it's going to fall in the do not reject region. So you can see that there's a lot of things coming back that are similar to what we've done in the past. It's just a different distribution, and they found these distributions by, you know, trial and error, and someone along the way said, hey, you know, there's just not one distribution that works for these. There's a huge variety. All right, so we have 7 degrees of freedom in the numerator, and so if you can see my sheet here, that might help you out a little bit. I don't know if you'll be able to read it if you don't have your own. All right, so here's 7. I'm going to go right down here to highlight the 7. Okay, so you wonder where the alpha is, because on all of our other tables, they gave the alphas up here. And this is the area in the right tail. But because we have a 2-dimensional table and we need degrees of freedom in the numerator and degrees of freedom in the denominator, they had to figure out some other way to give you the alpha. So you can see here, for each of the numbers of the degrees of freedom in the denominator that they give you 1, 2, 3, 4, 5, our 5 most common alphas. So locate the alpha and then follow that row over, because all of these are degrees of freedom in the denominator 50. And then in here, degrees of freedom in the numerator 7. Okay, see if you can find the critical value with this table segment that you have in front of you. Okay, good, and there it is. Alpha is 0.01, just follow that all the way over, and you get to 3.02. So to complete my picture, this number right here would be 3.02. So any test statistic that we calculate that takes us higher than 3.02 would put us over here, and then we would reject the null hypothesis. All right, we will be coming back to this as we do additional problems. And so we'll look at more examples for this. All right, now let's go into the ANOVA test. And if you recall, last time we looked at, we're now moving into chapter 12, which was a section where we looked at multiple proportions that were arranged in a contingency table. And, you know, depending upon the size of the table, you can have 4, 6, 12 different proportions that you would calculate, conditional proportions that you would calculate in a problem like that. In section 13.1, we're going to be testing claims about not proportions, multiple proportions, but multiple means. And usually we have smaller size groups. It's 2 or more means, but most of our problems, we might have 3 groups or 4 groups, but we don't get, or maybe even 5, but we don't get much larger than that. All right, so here's what it is. Let's just say we have 3 groups. We're going to define a variable k to be the number of groups. And all of these numbers that I'm defining for you will help you find the critical value and will help you identify the degrees of freedom. So here it is. Let's say we have 3 groups. The 3 groups are independent. So it's like section 10 or 11.3 where we had 2 groups and we were comparing means. In this one, we have 3 different populations, population 1, population 2, and population 3. And what we're going to do is we're going to take a sample from each of those independent populations. Knowledge of one sample gives us no information about the other. So we're going to take a sample. Now, what we're interested in here is testing claims about more than two means. And so for each one of these groups, what you want to report, the summary statistics, will be the same statistics that you reported when you had two groups. You want to report the mean and the standard deviation and the sample size of each of the three groups. Mean, standard deviation, sample size. And the only thing that's going to change in these variable names are the subscripts, or is the subscript. Group 1, Group 2, Group 3. And it's really these means that we want to look at. If there's a big difference in those means, then there might be a big difference, a significant difference in the groups, in the population means. What also comes into play here are the standard deviations, or the variances, which is the square of the standard deviations. All right, so that's the kind of the preliminary work. We're also going to see, just to give you some upfront statistics that you're going to want to identify, you're going to want to identify the N, and we would call this the pooled sample size. That is, treat all groups as just one big sample, and then to get N, you're just going to add the sample sizes of the three groups. If you had 4 groups, you would add N1 plus N2 plus N3 plus N4. But in this case, we have just 3 groups, so we're going to add the 3 sample sizes to get the overall sample size. And it's from these two that we identify the degrees of freedom. And there are 2. The degrees of freedom in the numerator is going to be equal to k minus 1, the number of groups minus 1. It's always going to be a whole number because the number of groups is always a whole number. And it's going to be a relatively small number. And the degrees of freedom in the denominator is this pooled sample size minus the number of groups. So if you were to add those two, you have k and negative k would cancel out, and you'd end up with n minus 1. It's kind of similar to n minus 1 degrees of freedom in a t-test. All right, so that information you can find from the summary statistics and the knowledge that there's 3 groups. And then all of this would set you up for the classical approach, because then you could go find the critical value. All right, let's go to step 1 now, and let's go through the 5 steps of a hypothesis test, so you can see how this test is going to be different than tests that we've done in the past. The null hypothesis, okay. There was a test in the previous section, test for homogeneity and proportions. We use that if we have only 2 categories of the dependent variable. In this one, the hypotheses are going to be set up in a similar way to that one. Our null hypothesis is always a statement that there's no difference. And since we're comparing means, we're going to say that no difference means that all of these means are exactly the same. These are population means. If you had 4 different groups, you would have to tack on to the end of the null hypothesis here equals mu4. And you certainly want to define the 3 groups. And you'll start these off with the mean, because they're all means. Now, to a competing hypothesis to the statement that all means are equal, all you need to negate that all the means are equal is just to find one of them that's not like the others, that one that's different than the others. So we're going to write the alternative hypothesis out in words like we did in section 12.2. And we're going to say something like at least one mean is different than the others. And when you're looking for something to, and again, this is one of those tests that it doesn't tell you which mean is larger, which population mean is larger, which population mean is the smallest. It just says that there's a difference. So you really need to look into the data to see what that difference is. So in your conclusion, you want to be more specific and say, if you do accept, or if you do support the alternative that one of them is different, you want to say something like, oh, this one is much higher than that one. All right, step 2, no difference here. This is always the step where we identify the level of significance, and that's the alpha. 0.05, 0.01, 0.10, some small number. Probability of making an error when we reject the null hypothesis. Okay, so you have these notes in the in e-learning from section 13.1. And if you just take those 2 words, or those 2 letters, and then that letter, and those 2 letters, ANOVA. It's an acronym. And this test is quite different in the calculator than our other ones. But here's what you're after. The means are the same, and so all 3 distributions look like this, and all the means are right in the middle. Or at least one of them is different. So in this one, we would say clearly the smallest one is different than the largest one. mu2 is larger than mu1. Now, what we could do is we could do a t-test on every pair that we have. We could compare the first group with the second group, the first group with the third group, and then the second group with the third group, and do a t-test on all of those to see if there's a difference. But what we do instead is one test, and we look at all 3 together. Here are the assumptions that we are going to make on this test, and we'll assume generally as we go through the problems that these assumptions are made. And one of the assumptions is that all the variances are about the same. The spread in the data, all about the same. You're not going to have one group that's spread out way out here, and then another one where all the data are spread out here. You want the spread in the data to be about the same. You also need that the populations from which you're drawing the sample are approximately normal. Okay, let's go to step 3. And this is where we gather the evidence, run the calculator function. In these problems, you're going to be given the raw data of 3 different groups. And so what you want to do is you want to enter numerical data for each group in a different list. So in our case, we have 3 different groups. So we want to enter data into our calculator in L1 for the first group, L2 for the second group, and L3 for the third group. This is what you need to do. I mean, in our previous test, the setup was that you had to enter in all the frequency data into a matrix. In this case, you have to enter in all the numerical values for each of the 3 groups in the 3 different lists. And then the calculator function that you're going to run, it's actually called ANOVA. And what you have to specify in here, the inputs, this test is going to be different because it doesn't take you to a special input screen where you can just type in some things. This one, ANOVA, goes to your home screen, and then you need to type in L1, L2, L3. If you had 4 groups, you would want to tack on L4 onto this. And then enter, and the calculator will give you the F, which is the test statistic, and P, which is the p-value. There's also the classical approach, and I drew the graph earlier, so I'm not going to draw it here. The F is the mean square treatment divided by the mean square error. And then the mean square treatment is equal to the sum of squares treatment divided by the degrees of freedom in the numerator. And the bottom number, mean square of the error term, is the sum of the squares of the error term divided by degrees of freedom in the denominator. Now, these sum of squares here, these are the difficult calculations because these are, this is the variance between the groups, and this one here is the variance within each individual group. And so the sum of squares of the treatment group is a variance. So if you remember how we calculate a variance, we take the sum of each, well, this is between mean, and then we're going to subtract, and this down here is k minus 1, the mean of the means. Maybe I'll put a double bar over that one, squared. So you have 3 groups, so you have 3 sample means. If you took those 3 sample means and took the average, added them up and divided by 3, you'd get the mean of the means. All right, so I'm not going to get into the weeds this far, but I just wanted to show you where these come from. And then the sum of squares of the error terms, this would be another variance where you take each data value and subtract the mean, and then square it, and then divide by n minus 1. And this would be where you pool all the individual data values. Let's say you have 10 data values in each of the 3 groups. So you would want to subtract each of the data values by its corresponding mean of that set and sum all those up. All right, so you can see how it would be somewhat of a tedious test statistic to calculate by hand. But this is how it is. And I wanted to define these because when you see the calculator output, you're going to link them to these variables. The calculator output is quite extensive. Okay, step 4, make the decision. There's no difference here. You can use the decision. You can make the decision using the classical approach if the test statistic falls in the critical region or not, or you can use the p-value approach. And then the conclusion. Basically, the conclusion here is you're going to say, yeah, there's evidence to support the claim that at least one of those means is different, but that doesn't give us enough detail. We want to be a little bit more descriptive than that. We want to say something like, oh, not only were they different, based on our observations, we see that the mean of group 1 is much larger than the mean of group 2. And if you really wanted to do more research, you could actually run a t-test between group 1 and group 3. All right, so let's apply this to a problem now. And let's see. I think I defined most of this stuff. If the p-value is low, the null must go. Okay, and then here's the calculator. I think I've given you this already. But on the last page, you have a couple of examples. All right, so let's go ahead and do the soybean yield. And for this one, the data represent the number of pods, plants, on a random sample of soybean plants. All right, so the farmer has a lot, a bunch of pods, and trying to figure out, which plants survive the best in Liberty or no-till or chisel plowed. So I guess this is 3 different ways to work up the dirt to plant these plants. And so they look at different pods with the different kinds of plots. Did they not till it at all? Did they till it Liberty? I'm not sure what that means. Or did they plow it with a chisel? And then these represent the number of pods that they observed on the different plots. And of course, bigger numbers are better. We want to see more plants, more pods. then less. So we have three different groups. We have group 1, group 2, and group 3. And they have, all of these different sectors, and they count the number of pods in each sector after working the soil up in a certain way. Okay, so what you notice, and what we're going to do just by looking at the data, is to calculate the K and calculate the N. And then we're going to identify the degrees of freedom in the numerator and degrees of freedom in the denominator. Then we're going to go calculate the mean and the standard deviation and sample size of each group. That'll give us all the preliminary stuff we want. Then we're going to go run the hypothesis test. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have 9 of the first type, 9 of the second type, and 9 of the third type. And together, N equals 27. Just add up all those little n's. All right, and K would be the number of groups. And in this case, we have 3. So degrees of freedom in the numerator is equal to K minus 1. So if you take the K, which is 3, and subtract 1, you get the degrees of freedom in the numerator. Degrees of freedom in the denominator would be N minus K. So here we're going to take 27 minus 3, and that's going to give us 24. Now we might not have a row or a column for 24, so we might have to estimate what the critical value is. All right, let's go calculate X1 bar, S1, and N1, X2 bar, S2, and N2, and X3 bar, S3, and N3. And the only way to do that is to enter in this data into your calculator. All right, so go in and clear out your 3 lists and enter in those 27 values in 3 different columns. L1 is the Liberty group. I think you'll find in this section that most of your data sets are small, your N's of the individual groups. Now you can calculate these one at a time. If you go to stat and then one variable statistics, you just have to change the list that you're doing the single variable statistics for. So the first time through, I'm going to choose my X list to be L1, and then I'll write down the mean and the standard deviation and the sample size of the first group. So let's see, 35 point, and I'll go 3 decimal places. Standard deviation, 3.257, and we know that the sample size is 9 for each of the 3 groups. Then we're going to run the same thing, but on L2, 34.778 and 5.044. And then do the same thing on the third group, 30.444 and 4.825. All right, so this is kind of the upfront work, because again, when you can see the sample means, which is really what you want to say, there's a difference in the means, but you can see that the standard deviations are, around the same area, 3, 4, 5, somewhere in there. If there is a difference here, then it's probably going to be between the first and the third group, because the means are most different between, this is the smallest one and this is the largest one. So later on, if you do find a statistically significant difference in these groups, you're going to go on to say that it appears that the average number of pods using the Liberty method is going to be larger than the average number of pods in the chisel plowed plots. Okay, so that's the upfront stuff. Now let's go ahead and go through the 5 steps. So step 1 are the hypotheses. And the null hypothesis in this case, since we have 3 groups, will be as we've defined the first one. All three means are the same, and the alternative is at least one of the means above is different than the others. This allows there to be differences in all three means. All right, so mean pods in plots using Liberty, and mu2 would be the mean pods using, that's the next one, the no-till, that's mu2, and mu3 is the mean pods using the chisel plowed. So just be sure that you define the different variables. Level of significance, usually they give that to us in the problem. We're going to look, and we don't see anything there. So we're going to specify the level of significance to be 0.05. All right, I'm going to do the classical approach, and I'm going to do the p-value approach, just so in this example that you can see the two different approaches. So classical and p-value. All right, first a quick one. The quick one we need because we need the test statistic anyway, because we're going to plot the test statistic on the classical method graph. So let's go ANOVA. And since we have three groups, L1, L2, L3, and then we're going to hit enter, and that's going to give us the p-value and the test statistic. So then we're going to write down all of the information from the calculator. All right, so all of our tests are in the stat test menu. This one is no different. So if you go to tests, and I think ANOVA may be the very last one there, H. So notice it goes to your home screen. And then we type in second and the number 1 to get L1. The comma is right above the number 7. And then second and the number 2, another comma. And then second and the number 3, and then close it off. All right, they give you a lot of stuff here. And let me write them all down. You have F, which is 3.766. I'll round to 3 decimal places. This is the test statistic. The first number that they give you in these tests always is the test statistic. The next one is the P. This is the p-value. All right, then they have something like factor. And sometimes they call this the treatment. And sometimes they call this between groups. What else? Numerator. So all of these are related to the top number. But our calculator calls it factor. Other outputs that you'll get from Excel or SPSS or others will call it something else. All right. So the first DF that they give you is the degrees of freedom in the numerator. And remember, that's always k minus 1, and we've already calculated that to be 2. So the calculator just confirms that we knew what the degrees of freedom would be. They give SS, which is the sum of squares of the treatment group, to be 148.963. And then they calculate the mean squares. And the mean square is equal to the sum of squares divided by the degrees of freedom in the numerator. So if you took the 148.963 and divided by the 2, you would get the 74.481. All right. Notice that there's an arrow indicating that there's more down there. All right, so let's go down there, and we're going to get the same 3 measures for the error term. This is known as the within group variance. And this is related to the denominator. All right, so the degrees of freedom that they post underneath this heading is really the degrees of freedom in the denominator. And we know that this is n minus k, which is 24. We've already calculated that. Let's see, 24. All right, the sum of squares in this case is the sum of squares in the error term. And that's going to be equal to 474. This is the hard one to calculate. If you were to do it by hand, I mean. And then the mean square would be the mean square, the error term. And as before, this is the sum of squares of the error term divided by the degrees of freedom in the denominator. So if you took that 474 number and divided by the 24, you would get the 19.778 number. And here they give the pooled variances. If you pool all the variances, what would the pooled variance be? Instead of just treating these 27 data values as 3 different groups, put them all together, calculate the variance, and there it is. We're not going to need that number. Okay. So know a couple of these relationships, know how to calculate the mean square if you're given the sum of squares. All right, and then the classical approach, we're going to have the F distribution with degrees of freedom in the numerator equal to 2 and degrees of freedom in the denominator equals 24. Zero is going to be over here. Same two regions, the reject region and the do not reject region. And then we need to find this critical value by going and consulting the F table. And you're going to find that it's not always easy to do that because we don't have all the possible degrees of freedom in the numerator, degrees of freedom in the denominator. But let's take a look. All right, so I'm going to get this table out again. Degrees of freedom in the numerator is 2. So we're coming down here. Degrees of freedom in the denominator is equal to 24. So I have to come down here, and the closest one I have is 25. So 24 is not listed here, but if it were listed here, it'd be between 20 and 25. So what I'm going to do in this column for degrees of freedom in the numerator equal to 2, I'm going to identify the 0.05 in both of these two. Okay, so here's the 0.05 if the degrees of freedom in the denominator was 25. And here is the critical value that we would use if the degrees of freedom in the denominator was 20. And so since 24 is somewhere between 20 and 25, the critical value that we're interested in is somewhere between 3.49 and 3.39. Now, it doesn't narrow it down to a single value. And so what we're going to say when we report this is we're going to say that this critical value here is somewhere between 3.39 and 3.49. This one would be degrees of freedom in the denominator equals 20, and this would be degrees of freedom in the denominator equals 25. So what we really have in our graph, I can't put one number here, but I can put 2. And so the only way that we wouldn't be able to make the decision using the classical approach is if we somehow found a test statistic between these two numbers. So anything less than 3.39 would put us here, and anything greater than 3.49 would put us over here. So if we get a test statistic that's equal to, say, 3.4, that puts us right in there, then, it's going to be difficult to use the classical approach. But that's okay, because we have the p-value approach. Okay, and you can see that our test statistic here, F, is 3.7, so it's going to be larger than both of these. So it's going to be sitting about right here, 3.766, and this is our test statistic. So you had to run the calculator function to get the test statistic anyway, so that you could plot it on your graph. Test statistic is something we always calculate in step 3. Okay, so we're on to step 4, and we're going to reject the null hypothesis because p is less than alpha. Our p value was 0.038 and our alpha value was 0.05. So p is definitely less than alpha. And you can also say that the test statistic fell in the reject region. Or you can say f of 0 is greater than f of 0.05. Right, you'd have to look at the graph to see that. All right, and then the conclusion. And so we're going to say that there is evidence to support the claim that there is a difference in average pod yield, we'll call it, when using the different, what do they call it, plot types. All right, now we're going to go on to say what that difference is. And since we do know that there's a difference, it's probably because the Liberty type is greater than the chisel cloud type. So we'd want to say that. All right, something like this, but in your own words, make that last statement. The Liberty plot type seems to yield a higher number of pods on average than the chisel cloud plots. And we could actually do a t-test on those two, and we would probably see a statistically significant difference. So the t-test that we would use is the 2-sample t-test. And I think it was between L1 and L3. We just do not equal to, calculate. And you can see the test statistic is 8 standard deviations below the mean of 0. And then this p-value is tiny, 9 times 10 to the negative 7. So we see a statistical difference between the first group and the third group if we just use a t-test. So by doing the t-test, you can confirm that the two groups we said were different are in fact different. Okay, we're not going to have enough time to do this one here. However, what I'd like you to do is to write in the chat, K, N, degrees of freedom in the numerator, degrees of freedom in the denominator, and then the critical value. And let's assume that alpha is equal to 0.10. Okay, so can you give me those 5 numbers? This is how you're going to start off every one of these. All right, let's start with K. Go ahead, in the chat, write the value of K. All right, so birth by day of the week. We have the weekdays, and an obstetrician knew that there were more live births during the week than on weekends. Interesting. She wanted to determine whether the mean number of births was the same for each of the 5 days of the week. Okay, so she randomly selected 8 dates, 1, 2, 3, 4, 5, 6, 7, 8, for each of the 5 days of the week and obtained the following data. So these represent the number of live births. Okay, so on Tuesday, on this one randomly selected Tuesday that they selected, there were 11,621 births. I imagine that this was in the United States. And then they randomly selected other Tuesdays. And then they selected 8 Mondays and 8 Wednesdays and so on. Okay, so that's what the data mean here. Okay, okay, good. All right, now go calculate the N. N is next. We would have N1 equals 8, N2 equals 8, N3 equals 8, N4 equals 8, N5 equals 8. N equals, good, 40. Okay, next one. What is the degrees of freedom in the numerator? And the formula for that is k minus 1. Okay, very good. 5 minus 1. And the degrees of freedom in the denominator, that's the n minus k. Okay. That's 40 minus 5, 35. Right? And if you add those two together, you get 39. 39 is one less than the 40. Okay, now the critical value. All right, so we're going to see the table for this one. And this is another one where maybe the best thing that you can do is you can get it close to or between two numbers. So you might want to write it in the chat like this. F is somewhere between this lower number and this upper number. You need degrees of freedom in the denominator, 35, and degrees of freedom in the numerator, 4. And then the alpha that we're going to use is 0.10. I'm not sure if you have the table, so I'll throw it up here. Okay, degrees of freedom in the numerator, 1, 2, 3, 4. So we want this one, or we want this one. So both of these have degrees of freedom in the numerator, 1, 2, 3, 4. All right, and then this table here just has degrees of freedom in the denominator that goes from 1 to 8. So we want that one. And then this one goes degrees of freedom in the denominator up here. So it just so happens that we don't have 35, but we have 25 and we have 50. So 35 would be somewhere in here between these two numbers. And the 4, here is the column for the 4. So focus in on these. There's a freedom in the denominator, 4. And our alpha this time is 0.10. So we have to go over here, select that number, and then we'll go from 25, go over here and select that number. So you can see 2.18 and 2.06. So the best that we can do here is to say that our critical value is somewhere between 2.06, the smaller of the two, and 2.18. This is degrees of freedom in the denominator equal to 25, and this is the degrees of freedom in the denominator being equal to 50. And so our 35 would be somewhere between those two.